It says going live. It says going live. It says going live. It says you're live. Hey, let's go. Um. Oh, my hand hurts. I told someone that I've been keeping away from like firefighting. Not firefight. What? That I've been keeping away from league. Or I've been playing games too much, and like how it feels good that I've like stayed away from games. Like I limited myself to one a day because like today I goddamn was attempting to play some more, but I didn't, and it's like yes, I'm keeping it up. It's tempting every day, but it's like like still sticking to that one day. So it's nice. And like I was saying, what I always say to everyone, it's like it's a small thing. I know it's a small thing, but and then like they finish my sentence for me. They're like, yeah, but it's huge though, right? And I was like, yes, exactly. And I was like, feels good. And then I don't know. I was like, oh no, I haven't studied all day because I ended up fixing the blinds finally, and I fixed the TV because the TV was broken. I thought it was broken. Turns out I just accidentally hit a freaking switch. Oh my god, it died inside. I was so whatever, silly mistakes, man. But yeah, so I kind of wasted time like fixing that, but at least it's a good thing to waste time on rather than on YouTube or something. So yeah, but yeah, no, I need to catch up on study now. So I'm gonna study. Yeah, no, like I sat down to study and then like I don't know, just that put me in a good mood, a focused mood. I've eaten a bit, and yeah, no, I just feel good. I got a lot to catch up on, so let's get started. Stop dilly dallying. Well, yeah, and thank you, Richard, for your comments of like saying, "Hey, I need you to live stream because it motivates me to study. Because motivating you motivates me to live stream, which is, this is a funny, nice little positive feedback loop we got going on. I'm a little sleepy though, but it is what it is. I gotta wake up tomorrow though, so let's see. I'm a little scared of getting distracted by music, so sorry if I don't play music. I might sleep early. I might just do work. Just do it and see what happens. You know? Yeah, bros. Okay.
So this is about the origin of life and the last universal common ancestor.
Origin of life.
Last universal common ancestor.
Oh, shit. Oh, it feels good to write. Hell yeah. Oh, pardon me, pardon me, pardon me, pardon me, pardon me.
So this is about the origin of life and the last universal common ancestor. Last universal common ancestor. Last common ancestor. So this is about the origin of life and the last universal common ancestor. Last universal common ancestor. Last common ancestor. Came from something. And of course we know that this is our timeline. We know that we are the last second, 24-hour clock, or 12-hour clock. Excuse me. With animals coming around. Carriers, evidence for the origin of living things happened very soon. Okay? After the Earth cooled. The Earth is about 4.8 billion years ago. About 3.8 billion years ago. There was evidence for carriers. Fossil evidence. Things that look like they might have been mechanical crystals, something biological. Stromatolites, a little bit later than that. Stromatolites structured today by cyanobacteria were around very common in the past. Indicated that cyanobacteria around then. Those cyanobacteria produce oxygen. At a certain point, the oxygen levels are about the same as they are now. Atmosphere of oxygen produced by cyanobacteria. And of course, eukaryotes came about. Single-cell eukaryotes. But what's interesting is that soon after the Earth formed, bombarded by meteors and all this debris coagulated around the sun, life started. You went from chemicals, rocks, to living things that can descend, that can modify themselves and natural selection. How did that come about? Well, if you look at life, there's periodic things about life. There's periodic things that can descend. And they can modify themselves and natural selection. How did that come about? Well, if you look at life, there's periodic tables about life. There's a periodic table of elements. This is the elements found on Earth. Some of them are very rare. Some of them are very common. Some periodic table where we have lithium, carbon, nitrogen, oxygen. Of course, the sun is nice and made hydrogen, helium. You can actually look at the abundance of this. And this is a periodic table of abundance. Of course, most of the universe is made of hydrogen. And a lot of it is a product. This fusion we have with normal stars. And short stars, big enough to explosions. All the other atoms got that's why we are made stars, right? And if you look at the abundance, obviously, 80% is helium, it's hydrogen, some helium, and then these are the other most abundant. You can't even see some of the other stuff, right? What's interesting is the most abundant molecules in the universe also happen to be molecules of the music. It's not like something weird made out of strontium and uranium and lead. Right? Life is made out of what's common: hydrogen, carbon, nitrogen. Most common helium. Here, use for anything. Right? It's made out of what's common: hydrogen, carbon, nitrogen. Most common being used either used for anything like this. It's not a miracle that we are made out of stuff. Most common used. So how do you determine what the characteristics are of the last unit common ancestor? Just like you do with characteristics of animals, you have characteristics of anything. We share common. It's like shared common. And so, yes, there are shared characteristics. There are a whole bunch of amino acids. There are 5 nucleotides. RNA, ATG, and C for DNA. There are some enzymes that are very, very common. Somewhere, this is the first thing that tells us about lack of common ancestry. You can make, there do exist, right? Modify. Because they have common ancestry, we just carry them. Whatever life was, because they have common ancestry, we just carry them. Modify. Where? This is the first thing that tells us about lack of common ancestry. I mean, you can make, and there do exist, right? Modify. Because they have common ancestry, they just carry it down to their parents. So whatever life was in the past, however many times life started, we only have one descendant that led to everything that's alive today. 20 amino acids. Acids, 5 nucleotides, acetyl-CoA, a couple of other enzymes, products, called proteins. That's how you always have. Look at the descendants. What do they share in common? That's a good guess. What the answer is. It's fish, of course. Also something else, but the problem is nucleotides and proteins doesn't include DNA. DNA is doing it. It's not functional. These proteins keep copying stuff, and the only thing that DNA can do is make proteins. The only thing you need for all those. process energy. Do anything, right? It's not something else. Sources, anything else. Also something else. Right? The problem is nucleotides and certainly DNA. DNA doesn't do anything. Right? It's not functional. These proteins begin to copy themselves. And the only thing that DNA can do is make proteins. One of the things you need for all those processes is energy. So you need energy to grow. You need energy to combine molecules. You need to store things. Right? You need to express that information. So somehow an inert molecule like DNA needs to produce a phenotype. Right? So how did that come about? Right? And there are several hypotheses. Right? One of them started out. Right? You need to store things. Right? You need to express that information. So somehow an inert molecule like DNA needs to produce a phenotype. Right? So how did that come about? Right? And there are several hypotheses. Right? One of them started out very early, showing that amino acids and nucleotides can be produced in organic material. This is a famous experiment. By Stan Miller and his supervisor. Basically, they just put together all these ingredients together for life. So things like ammonia, CO2, oxygen, a few other things, and they show them simulating electrical storms. And they did that for a long time, and they ended up with amino acids. So one thing they showed is that organic molecules can be made from organic molecules very easily. Right? So this idea that organic molecules are magical, you couldn't be made from nothing. It's true. The problem with this is it's been shown to be incorrect because they have the wrong ingredients in here. These things are not quite clear. But it shows organic molecules could be made from organic molecules. Texas atmosphere was not correct. And of course, making nucleotides, making amino acids doesn't help, right? You've got to be able to replicate them. Not only replicate them, you have to concentrate them. Right? If you produce amino acids in the ocean, they just dissolve. So you need to concentrate them. We concentrate things in membranes right, within our cells. So the concentration of things inside the cell is different from the atmosphere outside of us. And of course, they need energy to do that. One of the other things that's very common in all organisms is we produce energy by making radiants. Right? So we think of making energy by enzymes breaking the molecule apart. So that generates energy. Glycolysis can make energy, can make ATP. So that's common in all of life. Make ATP. Most of it is made by breaking down molecules and pumping hydrogen ions across them. Right? This is mitochondria. When you break down sugar molecules, you pump hydrogen into the inner space between the outer membrane and the inner membrane, and you use that hydrogen gradient, electrochemical gradient, to make ATP, to make energy molecules. That's how things are made inside mitochondria. And that's how things are made inside. And that's how things are made in bacteria. It pumps out hydrogen and then lets it run back inside to make ATP. These gradients are everywhere, right? They're common for making energy molecules in life. Yeah, it's common in energy molecules in life. It's possible to be common access to that. How do you get about making something that makes energy without membranes, right? Without proteins? also associated with, how do you get mental something? It means energy, not membranes, right? Not proteins in that case. Also associated with these, so the hydrogen gradient works by moving electrons along the electron transport chain, and those enzymes contain iron and sulfur. The cytochromes contain iron and sulfur, so the cytochrome product because of the color, the iron and sulfur. There's critical ingredients in these enzymes, and all of these have iron and sulfur in their cytochromes. Somehow those cytochromes with iron and sulfur, right? So these iron and sulfur elements inside protein hold protein together, are critical for making these gradients. Where did this come about? Well, there's a few people that try to put protein together. Critical for making these gradients. So where did this come about? Well, there's a few people that try to understand this. And one of the ideas around alkaline vents. So these are hydrothermal vents deep in the ocean where warm water comes out. Water that has been hot further down and dissolves molecules, including iron, but also including hydrogen. And what happens is the iron and the sulfur precipitate, produce these columns precipitate where the hot water comes. But the surface, right? And it forms a gradient. It forms a gradient from the water that comes out in the ocean, right? Cold water in the ocean, low hydrogen, low pH, and water inside, coming out here. You have this gradient already of hydrogen or hydroxide, and you also have surface. So the idea, right, is that the ocean is alkaline, you build up concentration of hydrogen or hydroxide. And you also have surface. So the idea, right, is that the ocean is alkaline, you build up a concentration of hydrogen in the ocean, and you have this layer, sulfur and iron, that produces a barrier, and this produces a gradient where we could drive energy. Right? We could drive the production of ATP. Of course, you don't have these ATPs, you don't actually have the enzyme. If you were to produce a gradient, right, in theory, we could have, right, instead of having a membrane, we've got these crystals, and somehow something evolves that's able to change that gradient that already exists into energy. And from that energy, you can make ellipse again, which is different type of energy. That's in theory. And so this cytochrome, this is this, to change that. If you were to produce a gradient where this, so the idea is coming out of here, we have a gradient already of hydrogen or hydroxide, and you also have surface. So the idea, right, is that the ocean is alkaline, you build up a concentration of hydrogen in the ocean, and you have this layer. Sulfur and iron that produces a barrier, and these this produces a gradient where we could drive energy, right? Could drive the production of ATP. Of course, you don't have these ATPs, you don't actually have the enzyme. If you were to produce a gradient, right, in theory, we could have, right, instead of having a membrane, we've got these crystals, and somehow something evolves able to change that gradient that already exists into energy. And from that energy, we can make ellipse again, which is different type of energy. That's a theory. And so this cytochrome, this is this electron transport chain, these cytochromes contain iron and sulfur, and they come back hydrogen on one side as they move electrons in it. There's a guy called Bill Martin that calculate some of this kind of stuff. And what should happen in this video, hopefully it's loud enough. Okay.
This is a 5-minute film about the origin of water submarine hydrothermal vents. The Earth is 4.5 billion years old. Geochemists tell us that the water was present on Earth roughly 4.2 billion years ago, about the time when late heavy nuclear bombardment came to an end. Since the discovery of black smokers in 1978, deep-sea hydrothermal vents have influenced thinking on life's origin. Today, biologists think that a particular kind of vent, discovered in 2000 by Deb Kelly at a site called Lost City, might be more relevant for life's emergence than the original black smoker vents. The chemical conditions at Lost City are more conducive to life, not nearly as hot as black smokers, and richer in hydrogen, an important source of chemical energy. The geochemical differences between these two types of vents are substantial. On the right, a black smoker is shown. Black smokers sit directly on top of magma chambers at oceanic spreading zones. Water from the seafloor is drawn down into cracks in the crust. It comes into close contact with 1,200-degree magma and exits black smokers at roughly 400 degrees. That is too hot for microbial life. On the left, we see convection at Lost City. The water does not come into contact with magma, so effluent at Lost City is much cooler, around 70 to 90 degrees. In addition, a very important geochemical process that's been characterized at Lost City is going on. It is called serpentinization. During serpentinization, water molecules are reduced by iron, too, present in iron magnesium silicate rocks that make up the Earth's submarine crust. That produces molecular hydrogen, shown in white, which leaves the vent in the effluent, along with sulfur, shown in yellow. At the vent-ocean interface, sulfur precipitates iron, too, shown in black, and nickel, shown in green, to generate transition metal sulfides, which serve two important functions: catalysis and compartmentalization. The mineral microchambers have catalytic activity because they're made of transition metals, which are important catalysts in chemical industry and in microbes. Their large unfilled d and f electron shells can hybridize to make metastable bonds with carbon and nitrogen. Modern microbes that live in the Earth's crust fix CO2 using nickel. Schematically, CO2 binds nickel and is reduced by hydrogen to generate a nickel-bound carbonyl. In the next step, a chemically accessible metal group binds the same nickel atom. In modern metabolism, this is catalyzed by nickel atoms in the enzyme acetyl-CoA synthase. At origins, transition metal sulfides at a vent could have done the job. The carbon undergoes insertion to generate a carbon-carbon bond. The catalyst bound the secret.
Chemistry. The idea is that these specialized thermal vents are places where it's possible, right? And again, it's happened 4 billion years ago, and all we have is common things that descendants have. Common things that descendants have, including this energy, hydrogen, things that you can see in these specialized thermal vents. Also, sulfur nickel, sulfur iron especially, are important molecules that are involved in producing this hydrogen radiation. All energy comes from mitochondria, bacteria, and chloroplasts. So this is the idea that energy came first. You have to have that energy. Right? That energy came before you can do anything else. There's another idea that RNA came before DNA. This was hypothesized, and it's found that RNA can act as an enzyme. The problem with DNA and RNA is sort of inert. Right? What does the activity are proteins? Right? Proteins are enzymes that speed up chemical reaction. You put molecules together to break them apart. And so, how could you have DNA? Hey, it can be copied. Proteins make the DNA, make the RNA, and proteins make the DNA, copy the DNA. Right? And the idea is when they found that the intermediate RNA could actually act as an enzyme, right? The ribozymes, they're enzymatic RNA molecules, indicates that you can actually have both enzymatic function, protein function, and copying function, because RNA is a string of molecules, nucleotides, very similar, right? They copy the DNA from DNA. So you can actually have RNA doing both functions, and then evolution, more efficient enzymatic activity by the production of polypeptides linked together amino acids, and RNA is relatively unstable compared to DNA. More efficient and information, which is the copying of nucleic acids from RNA into DNA, actually information material, because it's intermediate, because it does both functions. It could have been the first thing. And this the idea is called a catalytic RNA group. The idea is that the RNA could have been the first thing, right? Because of that and this is an RNA molecule, right? So it's a string of nucleotides. Like the idea is that the RNA would be the first thing, right? Because it's enzymatic. And this is an RNA molecule, right? So it's a string of nucleotides, just like DNA, but it's usually single copy, single strand, and it folds on itself. It's folding. It's active activity. And these are called ribozymes. Yeah. Ribozymes are involved in removing introns from RNA. Ribozymes are involved in these things themselves, not done by DNA. The splices onto nucleotides. And experiments are done showing the ribozymes can actually copy. Right? Well, they can copy copies of themselves. They can make copies of themselves. So here's a ribozyme with a 5' end, a 3' end, and a 5' end. If you add the right ingredients, including magnesium and some nucleotides, you can actually make a copy of it. Because again, it's a single strand molecule with the ability to form complementary base pairs, just like DNA, so you can actually complement a new RNA molecule. Unfortunately, when these experiments were done, they also needed to add nucleotides to actually add protein. But there's a soft single.
So gassy.
Well, that was one of the people that showed this. That basically, what they did is the right side added particular regions and watched it copy itself. Here it is copying itself. The total amount of RNA, how much it transfers it to. Amazon, I actually had protein. But there's a Saul Spiegelman was one of the people that showed this. That basically, what they did is the right side added particular regions and watched it copy itself. Here it is copying itself. The total amount of RNA, how much it transfers it to. Not only does it copy itself, the RNA copies itself. For example, it has a particular function. You can actually see that the function changes. This infection unit, particular RNA actually turns into a virus, and you can actually measure mutations in that virus as it gets copied. Transmit information and can be modified, essentially modified. Very soft black as it gets copied. Transmit information and can be modified, essentially modification. Very soft black square base, right? Because you have to do these transfers by hand. In theory, the process is possible. Very as it gets copied. Transmit information and can be modified, essentially modification. Very soft glass square based, right? Because you had to do these transfers by hand. In theory, the process is possible that an RNA molecule can copy itself and it can change. And it can change for the better. It can change, in this case, it can change for less infection, but it just as easily change for greater copying ability or the ability to make other things. RNA world. Either energy came first or RNA enzymatic activity and information came first. Unfortunately, you kind of need all of these at the same time. You also need that membrane. So where was the membrane produced? It's made of lipids nowadays, membranes. And lipids need lots of energy and particular enzymes to be made. So was the membrane these surfaces of hydrothermal vents? It happened a long time ago. So it's kind of hard to imagine. These hypotheses lead to people thinking about experiments you could do, right? But whether those experiments ever resolve what happened 4 billion years ago. Even though we know these molecules are nothing special, they can be produced from inorganic material. We have this tantalizing information, shared characters, aggregations, no aggregations could happen. We know that RNA has enzyme and information, so all these things somehow involve in the origin of life. We molecule first, energy, membranes, energy first, radiance and ATP, or RNA first. It's a difficult one, right? Because it happened 4 billion years ago. We don't have any ability to actually replay that life. Just want to talk about this kind of idea of the 5 kingdoms of life that people think about. This is actually from a book showing that there's 5 kingdoms of life. We know that this is not the case. I'll only talk about this because it happened 4 billion. Energy first, radiance and ATP, or RNA first. It's a difficult one. Right? Because it happened 4 billion years ago. we don't have any ability to actually replay that life. So let's talk about this. I gave the 5 kingdoms of life that people think about. This is actually from a book. So the 5 kingdoms of life. No, that this is not the case. Paul Woes showed that there were at least 3 super kingdoms you call life that people think about. This is actually
Joyce is back. Yeah.
from a book showing that there's 5 kingdoms of life. We know that this is not the case. Paul Woes showed that there were at least 3 super kingdoms. He called them domains. There were the bacteria, there were other prokaryotes called archaea, and there were eukaryotes. And this is based on ribosomal RNA. Ribosomes contain RNA, it's enzymatic. Where translation occurs, the ribosomes also contains proteins. And you can look at the relationships. These share common ancestors of bacteria. There's a common ancestor of eukaryotes and archaea, but archaea are monophyletic, they're single origin, all ancestors, and these are eukaryotes. And I want to talk about 2 things. One is whether this is true, right? Whether all archaea are monophyletic compared to eukaryotes, and whether this is true. We have the these early branching, what's considered early branching, roots. There are these long branches. It turns out that these roots do not have mitochondria. But the idea is where do mitochondria come about? If you do the phylogeny of things, of organisms, you find that if you do ribosomal phylogenies, you get this kind of relationship. If you use another enzyme, bacteria and eukaryotes more closely relate to each other. If you get another gene and you look at the relationship, you find that archaea, bacteria more closely relate to each other than eukaryotes. And we talked about this, right? The way this happens, the only way you get incongruent relationships, bacteria get more closely related to eukaryotes, and eukaryotes more closely related to archaea. Unless it's gene transfer. The idea is that it's horizontal related to eukaryotes and eukaryotes more closely related to archaea. Unless it's gene transfer. The idea is that this horizontal gene transfer was rampant in early life. These things were swapping genes all the time. Genes produce proteins that had a fitness advantage. If you do the phylogeny of things, of organisms, you find that if you do ribosomal phylogenies, you get this kind of relationship. If you use another transfer. The idea is that this horizontal gene transfer was rampant in early life. These things were swapping genes all the time. Genes produce proteins that had a fitness advantage. S. And so you end up with organisms, right, that depending on what gene you look at, the gene could be more closely related to a bacterial gene, or the gene could be more closely related to an archaeal gene. Lots of that gene transfer. But there's no possibility, is that eukaryotes and micro. The idea is that this horizontal gene transfer was rampant in early life. Swapping genes all the time. Genes that produce proteins that had a fitness advantage. Mess. And so you end up with organisms, right, that depending on what gene you look at, the gene could be more closely related to a bacterial gene, or the gene could be more closely related to an archaeal gene. Lots of that gene transfer. But there's no possibility, is that eukaryotes and mitochondria occur at the same time. This is another video by mitochondria occur at the same time. This is another video by it's another way of explaining why half the genes are like bacteria and half the genes are like an archaea.
This is about the origin of eukaryotes. Though many different theories have been proposed to account for eukaryote origin, the simplest one in physiological sense inverts anaerobic syntrophy. In the example shown, the mitochondrial ancestor, shown in blue, is a facultative anaerobe and produces molecular hydrogen as a fermentation end product, which the host avidly consumes. Note the outer membrane vesicles, small blue spheres, being produced by the host. Vesicles of bacterial lipids fuse with the host's plasma membrane, anaerobe, and produces molecular hydrogen as a inverts in film about the origin of eukaryote.
It's another way of explaining why half the genes are like bacteria and half the genes are like an archaea.
This is a 5-minute film about the origin of eukaryotes. Though many different theories have been proposed to account for eukaryote origin, the simplest one in physiological sense inverts anaerobic syntrophy. In the example shown, the mitochondrial ancestor, shown in blue, is a facultative anaerobe and produces molecular hydrogen as a fermentation end product, which the host avidly consumes. Note the outer membrane vesicles, small blue spheres, being produced by the mitochondrial ancestor. When it becomes an endosymbiont within the archaeal host, vesicles of bacterial lipids fuse with the host's plasma membrane, giving it a mixed lipid composition. The endosymbiont can divide. Occasional endosymbiont lysis results in bacterial chromosomes in the host cytosol, gene transfer from endosymbiont to host, and genome chimerism. Gene transfer can occur over multiple rounds and carries some faithful hitchhikers, which become visible as we zoom in. Group 2 introns.
Eukaryotes have introns? They have nucleus.
In yellow.
What's the introns? What do they
Introns
do?
occur in bacteria, including the ancestors of mitochondria. They're self-splicing. That is, they remove themselves from the mRNA via a single round of translation. Once removed, they can reinsert into a new location and thereby proliferate in the host's genome. Group 2 introns do not impair gene expression in prokaryotes because ribosomes are active on nascent transcripts to remove the newly inserted group 2 introns. However, group 2 introns are the evolutionary precursors of the spliceosomal introns found in eukaryotes. In the evolutionary transition from group 2 to spliceosomal introns, group 2 introns underwent fragmentation into shorter spliceosomal introns, whose removal required activities in trans provided by intron-derived RNA components in the spliceosome. Shown here. The transition to spliceosomal splicing creates a severe problem though, because spliceosomes are slow on the order of minutes per intron, while ribosomes are fast on the order of 10 peptide bonds per second. The result is that the transition to spliceosomal introns inhibits gene expression at many loci simultaneously. Impaired gene expression at many loci in the nascent eukaryote effectively dooms it to extinction, unless a solution is found to the splicing problem. One solution would have been to delete all introns, which however did not occur, because spliceosomal introns were present in the eukaryote common ancestor. An alternative solution would be the physical separation of splicing from translation. Separation in cells usually means membranes, and here the membrane vesicles produced by the symbiont can serve a very important function.
The ER
Exclusion of active ribosomes from chromosomes via a novel membrane, the nuclear membrane, allows the slow process of splicing to go to completion in the absence of active ribosomes, so that the fast process of translation can be performed on intron-free mRNA in the cytosol. This generates nuclear cytosol compartmentation in the ancestral eukaryote. The evolutionary novelty that affords the new lineage is a cytosol that is free of active chromatin, a dedicated translational compartment where the world of eukaryote-specific structural proteins and protein-protein interactions can unfold. But by sequestration.
Oh, right. Sorry. Okay. So the idea, right, is if you damage these root 2 introns, because introns, remember introns are these pieces of DNA within.
But by sequestration.
Oh, right. Sorry. Okay. So the idea, right, is if you damage these root 2 introns, because introns, remember introns are these pieces of DNA within genes that have to be removed from the RNA. Like, they can't do it themselves, and they have to have a method to remove it. The way it's done. And with slices of introns, remember introns are these pieces of DNA within genes that have to be removed from the RNA. Like, they can't do it themselves, and they have to have a method to remove it. The way it's done is with spliceomes. Spliceomes is the protein, the RNA complex, remove these introns. But right, if you have translation, if you're trying to make protein, because you're translating as the RNA, is being removed these introns. But right, if you have translation, if you're trying to make protein, because you're translating as the RNA. RNA is being made as bacteria do. But right, if you have translation, if you're trying to make protein, because you're translating. As the RNA is being made as bacteria do. Right, they get stuck. So you have to separate and slice the slices on removing the intron from translation errors. So the argument is that that's why the membrane came about. The idea is the membrane came about to separate transcription, which is making RNA, and slices on removing the introns, all in the nucleus. The idea is the membrane came translation, if you're trying to make protein, which is translating as the RNA is being made as bacteria do, right? They get stuck. So you have to separate and slice the slices on removing the intron from is being made as bacteria do, right? They get stuck. So you have to separate and slice the slices on removing the intron from translation errors. So the argument is that that's why the membrane came about. Again, the idea is the membrane came about to separate transcription, which is making RNA. And slices on removing introns, all in the nucleus, and then the RNA is spliced, came about to separate transcription, which is making RNA, and slices on removing introns, all in the nucleus. And then the RNA is spliced to go into the cytoplasm, and then be translated. And this is occurs because of this fusion of the archaea with bacteria. Part of that explains why some genes in eukaryotes show bacterial origin, and some genes in eukaryotes show archaeal origin, because that's the origin of the eukaryote. It's the fusion of bacteria with an archaea. Bacterial origin, and some genes in eukaryotes show archaeal origin, because that's the origin. Part of that flux will go into the cytoplasm and then be translated. And this occurred because of this fusion of an archaea with a bacteria. Part of that explains why some genes in eukaryotes show bacterial origin, and some genes. In the eukaryotes show archaeal origin, because that's the origin of the eukaryote. It's the fusion of bacteria with an archaea. You also get to talking about the origin of meiosis in this, because part of that problem is that you also have to separate because now the DNA is inside the nucleus, and you have to separate that nucleus. You can't pass the membranes of the cell like they are in bacteria. So mitosis and meiosis had to evolve also. You can have that origin. You also have more, right? It's been found, archaea have been found in lots of places. They were first found in phosphates in very extremely now they're found everywhere. Turns out they found in deep sea beds, they found archaea. Here, T-A-C-K. Archaea that are more closely related to eukaryotes. T-A-C-K. Archaea that are more closely related to eukaryotes, share a common ancestor with eukaryotes, more closely related, and they are with archaea. Indicating that eukaryotes are this fusion of a bacteria with an archaea. So they're archaea, a common ancestor of eukaryotes, with an archaea that's more closely related to a bunch of archaea than the other archaea. And the paraphyletic group, so archaea is paraphyletic with respect to eukaryotes. Not all the ancestors of archaea are considered archaea. So now, instead of thinking 3 domains in life, there's actually 2 domains in life. There's archaea / eukaryotes. And there's bacteria. Origin of eukaryotes. Instead of being like this, where there could have been a common ancestor for both, but then there's a common ancestor of all the archaea, it turns out that eukaryotes are actually a common ancestor, share a common ancestor with archaea. Is made by the fusion of an archaea with a bacteria. That explains a lot of things with this lateral gene transfer. Right? Basically, the lateral gene transfer occurred during the origin of mitochondria. If that's the case, mitochondria had to be in all eukaryotes. And so the idea that these things don't have mitochondria are considered primitive, that means, right? And mitochondria occurred after they diverged, must be incorrect. In fact, it's more than that. It turns out that this diversification here is actually an artifact of sponge eggs. You see our long branches, they're very different from these. They call long branch attraction. These things, just by chance, have to be really, really different, and it phylogeny pulls them to other different things. And so these things, primitive, are are not. Right? They're not early diverging. In fact, microsporidia, if you consider one of the earliest branching things, turns out to be a fungus. And so these things. Primitive are not actually. These things is actually an artifact of genetics. You can see they're long branches. They're very different from these other things. Think of long branch attraction. These artifacts diverge. Have to be an all eukaryote. A lot of things. This lateral gene transfer. Right? Basically, the lateral gene transfer occurred during the origin of mitochondria. If that's the case, it means mitochondria have to be an all eukaryote. And so the idea that these things we don't have mitochondria. Is primitive at that age. Right? If that's the case, it means mitochondria have to be an all eukaryote. That explains a lot of things with this lateral gene transfer. Right? Basically, the lateral gene transfer occurred during the origin of mitochondria.
This is how many.
If that's the case, it means mitochondria have to be an all eukaryote. And so the idea that these things don't have mitochondria are considered primitive, at least, and mitochondria occur after they diverge, must be incorrect. In fact, it's more than that. It turns out that this picture here is actually an artifact of time space. You can see it on long branches. They're very different from these. They call long branch attraction. These things, just by chance, happen to be really, really different, and they biologically fool them to other different things. And so these things, primitive, are not. Right? They're not fairly divergent. In fact, microsporidia, which is considered one of the earliest branching things, turns out to be a fungus. So microsporidium, it's basically a parasite of humans, of vertebrates. If you look at it, it's actually it doesn't look like a fungus, but it's got a tight wall. It lives inside organisms. It's primitive. It's simple organism, less, but mitochondria lacks the job to live inside things. It's a parasite of vertebrates. That thing's divergent. It's certainly vertebrates, so it's got walnut. If you look at other genes, haven't changed as rapidly as RNA. Clearly shows this. Now, microsporidians. Cryptococcus causes some respiratory ailments in humans. There's a cryptococcus that used to be so much anymore, but used to be very important in HIV patients, AIDS patients, because we infect their lungs and cause death in immunocompromised people. And it turns out that microsporidians are actually just part of the fungi. They've just been simplified again. The idea that evolution was about anything, right? About complexity, increasing complexity, well, it's plenty of examples where reducing complexity. This is one of those cases. And the other, the early branching groups are in a group. They're called the excavates. They contain mitochondria containing things. Right? This is a group. It's eukaryotes. So the evidence is that the mitochondria are original, and this is a mistake. No, it's still in books. And those things that don't have mitochondria, they live inside organs. Using of oxygen, so mitochondria needs oxygen to make phosphorus, ATP, and then low oxygen, mitochondria. And so they have these organelles. People didn't know what they were, called hydrogenosomes and liposomes. They have a little bit of DNA. They don't do oxidative phosphorylation on mitochondria, but they do contain some of the enzymes to recycle ATP like mitochondria. Turns out these things are mitochondria. It's just one of the things it does. It uses hydrogen and produces, recycles acetyl-CoA. Recycles acetyl-CoA. Function that happens. in mitochondria also. It also has the proteins that transport it into the hydrogenous cells to the same transport signals used for mitochondria. It's clear that they're mitochondria. And just like most, it also has the proteins that transport it into the hydrogenous cells to the same transport signals used for mitochondria. It's clear that they're mitochondria. And just like most things, mitochondria have been lost in lots of organisms. And organisms, these are histamines, these are animals, and these organisms are lost. Mitochondria, this is microsporidiums, it's mitochondria, lost in lots of organisms. When you find yourself in an environment with low oxygen, you'll need oxygen. So in terms of character common ancestry, you look for shared characters always, right? Common characters in life, possibly proton gradients. That's a very common characteristic. So you have to get energy somehow. Proton gradients could be a way of doing it. You can also need enzymatic activity to speed up some reactions, and you also need a way of transmitting that. So the RNA could be the answer to that, could be an intermediate. Other evidence RNA is important is that RNA is used to make proteins. Ribosomes are RNA is Organ of life. I'm putting together questions for the test. Here, let's go back in 5 more minutes. So the questions you guys submitted. So this one, I think we'll talk about humans, talk about human evolution next. The reason is I'm trying to redo my human evolution lectures because there's a lot of stuff that just came out recently. Why is it so different class organisms? And part of the reason is because you can't find shared around here. You either have not done molecular work or shared. I think we'll talk about humans, talk about human evolution next. The reason is I'm trying to redo my human evolution lectures because there's a lot of stuff that just came up recently. Why is it so different in classifying organisms? And part of the reason is because you can't find shared derived characters. Right? You either have not done molecular work or shared derived characters, fossil things are difficult to find. There's no reason that any organism should be more difficult than any other. Apply an understanding of evolution to it. So why are some areas more research than others? Because usually there's some areas that people make money out of. So why are there conflicting opinions? It's a scientific question, right? Why do people have conflicting opinions? Because the evidence is ambiguous, right? Does RNA come first or did energy come first? It's happened a long time ago. There are people on both sides of the debate, right? They think the RNA came first and then somehow produced energy in some way. Like there are people who think that energy had to come first before we got transmission of information. Right? Is modern medicine halting natural selection? People talk about this, right? So evolution occurs all the time, right? It's called drift, people without natural selection. Populations change behaviors because some people live with phosphine, some people don't, by accident, like not all the time. Some people die because of medical conditions, right? Because they have particular conditions that are susceptible to infection, for example, from pathogens. You die more readily, right? Not if you have this gene, you will die, but the chances are it will be less offspring if you have these genetic variants if you don't have these genetic variants. So populations will change by natural selection, right? One of the things that's still being selected for in humans are resistance to diseases. Until we come up with ways of fighting these diseases that have nothing to do with genetic constitution. So our resistance to diseases will certainly change with time. Resistance to diseases and medicines to do that. You know, take 100 years, we can do that. You know, take out herbal medicines, it'll be a couple of 1,000 years. Humans just die of diseases like crazy. There's not enough time to change population with natural selection, right? Natural selection takes multiple generations. Resistance to disease is multifactorial. There are many, many genes involved. Every time we produce new offspring, we combine these genes in new combinations. It takes a long time. The frequency of those particular genes to increase in the population. It's just like selection, right? Selection is not something that happens overnight. Multiple generations. So it has to be a continuous force, selective force, affecting to a particular disease, right? Over many, many generations before we can build up a change in frequency of alleles, right? Due to selection. So where does evolution begin? Somehow, where the origin of life began. What's the likelihood of consciousness having evolved separately from here? I guess this means are there aliens that could come visit us? Well, why not, right? I haven't seen any yet, but it's possible, right? Evolution is not about progress towards consciousness. It's just about surviving in your local environment better than other people around. And there are plenty of planets where life could have started. In fact, life started from inorganic sources very soon after the Earth was habitable. Right? Very soon is a bad word, right? 300-400 million years. It's not very soon, right? But it's not unimaginable in the life of a planet that it could start again somewhere else. But why would you think there would be the origin of life would be lead towards consciousness? It's possible. There's no planet for it, right? They just sent another missile. They just sent another rocket to Mars looking for life on Mars. They've done it a few times, and they found nothing. And I'm just wondering what's going on. Why are they sending those? Just say something's going on. Maybe they'll send it to another part. Maybe they'll analyze it a different way, and they will show that there was life on Mars. But I'm not sure why. It was a wonderful. The first time the thing arrived on Earth, they were using CO2 production as a measure of life, and so they had this machine that picked up some dirt, and they mixed it with some chemicals that they got from Earth, and they thought there would be a reaction, and there's CO2 coming off. That would mean there was something metabolizing that substrate, and therefore it had to be life. It was a big fanfare for a few days, and they realized it was basically just reacting. It's a reaction, never no chemical reaction producing by CO2. There's nothing around the reaction. The experiment itself actually false from the beginning. They found a 100-million-year-old bacteria. So it's a deep sea core. Now, there's non-contaminated bacteria in the center of this core, from deep sea, and they revived 100 million years old. They revived some bacteria. It's ignored 100 million. That's true. That's back. How did the first animals evolve? I'm not going to talk about that because Pete's going to talk about the first animals. Part of the first animals are 80 atoms, which I didn't talk about. Part of the phylum of animals around today happened during Precambrian, and Pete's going to talk about Precambrian. Evolution is not obvious on a human scale. How fast does evolution happen? Well, it's not obvious on a human scale. It happened very slowly. And does math check out in how long life has been around? Yes. There's been experiments on this. So just one more thing. Eyes, for example. This is one of the creationist great ideas. Eyes can never evolve because you need to have a perfect eye to be able to what's good is a half eye. Right? You can't see anything. Right? And so they did, and there are organisms that have light-sensitive cells. So you have light sensitive, and then so what they did is they mathematically modeled. You have light-sensitive cells, and there will be selection, some selection coefficient of like 1% or even less. That's not the normal selection coefficient in nature. Very little change in that population. If you take a flat plate and you bend it, you can tell the direction more. Because there's light coming from this direction, you're not getting light on this side, you're getting more light on this. If you bend it more, you get more light on this side and less light on this side. And as you take that flat plate and curve it even more, right, you can tell which direction light's coming from. Because this side can get more light from there, and this side can get less light. Right? If you turn it more, you can actually almost focus. Right? It becomes like a pinhole camera. Right? And so they did that. They said, okay, a selection coefficient of 1/10 of 1%. How many generations, right, would be? And there are organisms that actually have all of those, right? So the flatworms have these light-sensitive organisms that are in these depressions. So they do exist as possible. And they found that you could easily fit it, right, within the evolution of life. That's Precambrian, 500 million years, 600 million years ago. Right? Just with a small change in the directionality of producing a more and more cup-shaped light-sensing organ. And proteins that are involved in our lens, and the proteins that are involved in producing the lens, are proteins for other functions, right? They're excitation. The proteins that produce themselves. Why would we have a protein that's layered to be able to focus light? Right? These are proteins that found in proteins that have other functions that have been used, exacted, right? They've been used for nothing, so they've been selected for something else, and now they've been used to make a lens. Right? So it's an ahistorical adaptation. They've been selected for some enzymatic functions. It turned out they can also be used for producing a clear lens. They can focus that light even more. There are organisms that don't have lenses and have very closed eyes, right? Little holes, so they can see, sort of. You can certainly tell when somebody's coming towards them, blocking the light. Right? So evolution does occur, and certainly can occur within the time frame that we know now the Earth is. Right? Maybe not the time frame that Darwin thought about, certainly not the time frame before Darwin thought the Earth was about that. Small changes over multiple generations. Those changes. I'm going to talk about human evolution on Tuesday and Wednesday. I'll give you the questions on Wednesday. And Thursday, we'll have a review session, and on Friday, you get your questions for your test. You have Friday and Saturday to write the answers and submit them. Anytime between Friday and Saturday midnight. I set up the turn in essay. I have to ask anybody to write. Okay. Next weekend.
Let's finish my weekend. Oh wait, it's my Tuesday. All right, I'm very tired. Got some study done. Adios, boy. Hope y'all doing good. K/O/good. Bye bye.